Hello again. We are moving on to 8.2, area of a surface of revolution. So what is this all about? Is assuming we have a function, let's say this function, we're going to look at an example in a minute, and let's say between 0 and 2, and we want to rotate this curve around the x-axis, about the x-axis. So we will get something like this, and we will get a solid of revolution. And what we are interested now is in determining the surface area of the solid. So that's what the area of a surface of revolution is all about. So we are going to look at two different situations. Situation A, when we rotate with respect to the x-axis, or about x-axis, in which the formulas that we're going to look at are the surface area is, of course, we are talking about the y equals f of x, and in this situation, let me write it here better, y equals f of x, and we have an interval between a and b. The function f is positive, and of course f prime is continuous. In order to be able to use or are allowed to use the fundamental theorem of calculus part 2. Okay, so the surface area will look like the integral from a to b from 2 pi f of x, the square root of 1 plus f prime of x dx, of course squared, dx. Of course, we can replace this by the Leibniz notation dy over dx. And then if we do that, then this becomes simply y. And we have s, the integral from a to b, from 2 pi y, and we are integrating this time with respect to y, and we have 1 plus dx over dy squared times dy. Okay. The other possibility is when we rotate with respect to or about the y-axis, about y-axis. When we rotate about the y-axis, the formulas are slightly different. 2 pi x and the square root of 1 plus dy over dx, of course everything squared dx. And if we integrate with respect to y, that will be the integral from c to d, assuming that y is between c and d, c to d, and 2 pi y, the square root of 1 plus dx over dy, everything squared, of course, dy. So this is what we have to keep in mind. Either we rotate with respect to the x-axis, and depending on what type of function we are given, if we are given y equals f of x, or we are given x equals g of y. So that's another possibility. And when we rotate the curve with respect to the y-axis, and we want to determine still the same thing, the area of the surface of revolution obtained, of the solid that we obtained by rotating the curve or the arc length, if you want, about the x-axis or the y-axis. So let's take a look at a few examples. And I'd like to start with number 9 on 573, and this is my page 2. Okay, so we are given y equals x cubed. We are given the limits for x between 0 and 2, and there we are told that we are rotating about the x-axis. Okay, so first let's find y prime, which is 3x squared. Let's find y prime squared, which is 9x to the 4th. And then let's set it up. So we are going to look at 2 pi, the function itself, which is x to the 3rd, the square root of 1 plus, and we have 9x to the 4th dx. So let's write that. The integral from 0 to 2, from 2 pi x to the third, the square root of 1 plus 9 x to the fourth dx. Notice that at this point, we have to use a substitution. I recommend let u be 1 plus 9 x to the fourth, where du equals 36 x to the third dx. Why did I choose that? Because I already saw that x cubed was there in the problem. Yes, you know my style. I prefer this is just a simple number. In some situations, I will have to solve for the x, but there is no way. There is no reason here. So I'm going to multiply by 36 and divide by 36, in which 36 and x cubed and dx, 36, x cubed, and dx, they will all be du. This is the square root of u, or u to 1/2. And of course, I have to change the limits of integration. So I have 2 pi over 36. So this is pi over 18. The integral from, again, 36 with x cubed with dx. And this is the square root of u, or u to 1/2 du. Limits of integration carefully. When x is 0, u is 1. When x is 2, we get, where's my calculator? What do we get? So, what did I have? 1 plus 9 times 16, 145. Good. So then this is pi over 18. U to 3/2 over 3/2 from 1 to 145. And finally, we have 2 pi over 3 times 18. I'm not going to multiply because I'm going to simplify in a minute. And this is 145, the square root of 145. That's the square root of 145 cubed. 145 comes outside, and there is still 1 inside. And minus 1. And here I will simplify. And I have, finally, pi over 27, 145, the square root of 145 minus 1. When I plug in 1, it's 1. Good. Let's choose the next problem. And I think we should look at 13. Yes. Okay. So 13 is on the same page, 573. We're given y equals cosine 1/2 x. We are given x between 0 and pi. And again, about the x-axis. Okay, fine. Okay, that's my page 3. Good. So let's do some prep. Y prime equals negative cosine 1/2 x times the inner function prime. Ah, sorry, I meant to write negative sign. But if I just do this, it's easier. Okay, so y prime equals negative 1/2 sine 1/2 x. Y prime squared is 1/4 sine squared of 1/2 x. With parentheses or without, maybe it's easier if we do put parentheses. Okay, now we have the integral from 0 to pi. We have 2 pi. Then we have y. Coming back to, where's my first page? Okay, here it is. Okay. Same thing. This is our function. This is what we just determined with plus 1, of course, and dx. Okay, so then that is a cosine 1/2 x, the square root of 1 plus this, which is 1/4, sine squared of 1/2 x, and of course dx. So let's see how we address this one. Okay. I'm going to find the least common denominator here, which is 4. and then take out the square root of 4. So 0 to pi cosine 1/2 x to the square root of 4 plus sine squared 1/2 x dx. Good. I'll simplify these two. I'll put pi outside, and let's see what we have so far. 0 to pi cosine 1/2 x, the square root of 4 plus sine squared of 1/2 x. Again, I don't know if it's really necessary, but maybe it's easier for you to see. Okay, so I'm going to let u be sine 1/2 x, and then du equals cosine 1/2 x times 1/2 times dx. So I do have the cosine 1/2 x, I do have the dx, I don't have the 1/2. Who cares? Very easy. 2 over 2. So moving on. So I have 2 pi, the integral from, so 1/2 with cosine and dx will be nothing else but du. And inside the square root, we have the square root of 4 plus u squared and du. Careful with the limits of integration, please. When x is 0, sine 0 is 0. When x is pi, sine pi over 2 is 1. Now we are going to jump directly to table of integrals. And that is on page 6, and this is number 21. And I'm going to write the answer. And this is my page 4. So let's write the answer. And we are getting 2 pi u divided by 2, the square root of 4 plus u squared, plus 4 divided by 2 natural log of u plus the square root of 4 plus u squared, everything from 0 to 1. And we get 2 pi and the square root of 5 over 2 plus 2 natural log of 1 plus the square root of 5 minus 2 natural log 2. When you plug in 1 and then subtract when you plug in 0. And that is the area of the solid of revolution obtained by rotating the given function between those limits of integration. Okay, I think we should look at 15 on 573. So this time we're given x, which is 1/3, y squared plus 2 raised to 3/2. Y is given to us between 1 and 2. And of course, this is very important about the x-axis still. So let's differentiate the x with respect to y. And we get 1/3 times 3/2, y squared plus 2 to 1/2 times the inner function prime, which is 2y. Simplify these. So then now dx over dy squared is y squared, and this squared will be y squared plus 2, or y to the 4th plus 2y squared. Good. So now we are ready to write the surface area, the integral from 1 to 2, from 2 pi y, the square root of 1 plus this, y to the 4th plus 2y squared, of course, dy. But notice that this is nothing else but y squared plus 1, everything squared. And then we get the integral from 1 to 2, 2 pi y squared plus 1 dy, because I took the square root from this. Okay, moving on to page 5. Okay, so this will be 2 pi, the integral from 1 to 2 from y to the 3rd plus y dy, or 2 pi y to the 4th over 4 plus y squared over 2 from 1 to 2. Okay, 2 pi, 16 over 4 is 4, 4 over 2 is 2, minus 1/4 and minus 1/2. And let's see what we get. So this is 2 pi, and then 6 minus 1/4 minus 1/2. The least common denominator is 4. So we have here 24 minus 1 and minus 2. I simplify. So 21 pi divided by 2. How are we on time? Almost, okay. I think we can fit in one more. Let's say 17 on 573. This time we have y equals 1/3 x to 3/2. We are given x between 0 and 12, and this time about the y-axis. Okay, so let's start with dy over dx, which is 1/3 times 3/2 times x to 1/2. So this is 1/2 or the square root of x over 2. Okay, so then when I square this, dy over dx square, this will be x over 4. Okay, so now let's write the surface area. So the integral, so s is the integral from 0 to 4. I'm sorry, 0 to 12. Yeah, 0 to 12. From 2 pi x and the square root of 1 plus x over 4 dx. In order to solve this, I will use a substitution. I prefer u equals 1 plus x over 4. Du equals 1/4 dx. I also need to solve for x, so I can replace it in terms of u. So u minus 1 equals x over 4, or x equals 4, u minus 1. Okay, so what I really need here is just a 1/4 to get the dx. So I will multiply and divide by 4. 4 divided by 4. So now what happens? This with this will be the du. X will be this. 2 pi is out. So 2 pi times 8, jump over all this. So 2 pi times 4 is 8 pi. Okay, the integral from, one more time, 1/4 with the dx is the du. The square root is the square root of u, or u to 1/2. X is 4 times u minus 1. And that's it. Now the limits of integration. When x is 0, u is 1. When x is 12, 12 over 4 is 3. 3 plus 1 is 4. So next, 32 pi. The integral from 1 to 4, I distribute u to 3/2 minus u to 1/2 du. And this is 32 pi. U to 5/2 over 5/2 minus u to 3/2 over 3/2 from 1 to 4. Okay, let's see what we get here. 32 pi 2/5 times the square root of 4 is 2, so that's 32 minus 2/3. The square root of 4, 2, so times 8, and minus 2/5, but plus 2/3. When you perform all these calculations, I got 3712 pi over 15. Thank you.